In this section, we're going to look at the nature of chemistry and the classification of matter. So we'll start out by talking about the scale of chemistry, how big things are that we consider as chemists. We'll talk about how matter is measured as chemistry, as a science, handles it. We'll look at pure matter on the macroscopic scale, and we'll look at mixtures on the macroscopic scale, and we'll also look at things on the atomic scale. So chemistry is the study of matter on the atomic and molecular scale, which is really, really small, and that's also known as nanoscale. And you've probably heard of nanotechnology, which is essentially technology done on the atomic or molecular scale. And if we look at this chart, it's a logarithmic chart, so each jump is a jump of 10 times larger. And so a sheet of paper is about 1/10 as large as a human. A human is about 2 orders of magnitude, or 1,000 times smaller than the Empire State Building. And if we look at chemistry, chemistry is handled down here, where we have molecules and atoms, frankly much more molecules than single atoms. And if you look at those, they are on the scale of around 10 to the minus 9th, maybe 10 to the minus 10th meters. That is compared to a bacterium, which is 10 to the minus 6th meters, so that's 4 orders of magnitude, and a millimeter, which is about the width of a CD. So you all know what a centimeter is about, and so a millimeter is 1/10 of that, and so that's another 3 orders of magnitude. So it's about 7 orders of magnitude, so 10 to the 7th times smaller than the width of a CD. So molecules are, in fact, really, really small. So because of that, one of the most important things is that molecules can't be seen with the naked eye. And so atomic things can't be seen with the naked eye, and they can't be seen with an optical microscope, which you may have used in, say, a biology class or a geology class. And so we can categorize things by their scale. The atomic scale or molecular scale or nanoscale are too small to be seen with an optical microscope. Microscopic means you can see it with an optical microscope, but you can't see it with your naked eye. And macroscopic things are things you can just see with your eye. So some examples, a soccer ball obviously is macroscopic. A grain of sand is small, but you can still see it, so it's a macroscopic thing. A bacterium is too small to see with your eye, but you can see it in a regular light microscope, so that's microscopic. And a methane molecule is smaller than you can even see with a light microscope, so it's nanoscale or molecular scale or atomic scale. Those are all synonymous. Chemistry deals at the nano or atomic scale. So when chemists look at things, they'll look at something like, say, a beaker of water. And the way chemists think about it is even though that's a bulk scale, a bulk or macroscopic scale sample, we actually think of it in terms of what the molecules are doing. And so we visualize these little tiny molecules that are too small to see, and we think about how they're acting as a way to explain observations we see in the bulk material. So the way we measure things, the way we know stuff as chemists, is we make some measurements on bulk scale. The majority of those are measuring mass, just how much things weigh, you do it on a balance, and attraction of things to magnets. Far more the top one than the bottom one. And also attraction to be honest, attraction to electric fields. Individual molecules and atoms interact with different types of electromagnetic radiation in different ways, and we make lots and lots of measurements about molecules and atoms that way. So we use visible and UV light, we use infrared light, we use X-rays, and we use radio waves and magnetic fields. These different things tell us different things about molecules. UV and visible tell us about how well electrons are held near the nuclei inside atoms and molecules. Infrared tells us how molecules vibrate, which tells us something about their structure, about their shape. X-rays tell us about the shape of molecules. They actually tell us where the nuclei of different atoms are within a molecule. And radio waves are used to probe the environments around individual atoms, which tells us something about what other atoms are surrounding an atom under study. A key feature about chemical study, which makes it both really interesting and challenging, as well as actually quite hard, is that we can't see these atoms and molecules. They're too small to see. So everything we know is based on implied information that we get from bulk scale and real-world types of experiments we do, that then we infer what the molecules must be doing for those measurements we do on our human scale that we observe for those. Okay, now we're going to talk about classification of matter. There's lots of different ways of classifying matter. You can talk about what state they're in. You can talk about what composition they have. You can talk about whether they're magnetic or not. You can say whether they're blue or red. You can say whether they're hard or soft. There's lots and lots of different ways anybody, not even a scientist, can classify matter, whether they smell good or smell bad, whatever. As chemists, we do this in a variety of ways, and we're going to go through a few of those ways. One is what scale a sample is on. If we're talking about the atomic scale, we talk about atoms versus molecules. So if you're talking about and classifying chemical entities on the atomic scale, it's whether the things are individual atoms or whether they're molecules. On the macroscopic scale, we talk about whether things are individual elements or whether they're chemical compounds. So we're going to look at each of these in a little more detail. On the atomic scale, we have atoms versus molecules, and atoms are individual atoms of different chemical elements. And so these are the smallest building blocks of matter that have the properties that the elements have. So carbon, oxygen, hydrogen, iodine. There's lots of other ones. And each of these has a name and a symbol, which you're no doubt familiar with. So when you talk about H2O, you know that that means that has hydrogen. Sorry about sniffling. And it has oxygen. And we have the collection of all of the different chemical elements on the periodic table, which we'll go into detail more later on. But there's about a little less than 120 different elements known now, many of which we don't really deal with at all as chemists. The ones up above, like around 107, are made in amounts too small to actually do chemical studies. But most of the other ones we've done a lot of study on. Another way of classifying matter is whether you have individual atoms versus molecules. And molecules are collections of atoms that are held together, and they're held together by what we call chemical bonds. And so sometimes you'll see this depicted this way, where you just have two atoms attached to each other that way, with overlapping spheres. And sometimes you'll show a little rod, or a little stick, that says you have an atom here and an atom here, and that stick represents a bond holding them together. The molecules actually look more like these ones here. They don't really look like these ball and stick models, but the ball and stick models are easiest to kind of visualize what's hooked to what. On the bulk scale, we have a similar thing where we have pure elements, which is a bulk sample which contains all atoms of the same element. This is a block of aluminum. All of these are aluminum atoms. And you have chemical compounds, which is a bulk scale containing collections of molecules, or sometimes extended structures, that all have a discrete ratio of different atoms, of atoms of different elements. So compounds contain more than one element. Elements contain just one element. It's an interesting thing that molecules can be formed either from single elements, so O2 contains only oxygen atoms, so it's an element still, as is ozone O3. But molecules also can form compounds can also be formed from molecules. So both single elements and compounds can be used to make molecules. Compounds can be of two main types, or two broad categories. One is what's called a molecular compound, which is made of lots of individual molecules. So these are CO2 molecules. So there's lots of CO2 molecules which look like this. That's one of these things. And there's lots of those all near each other making up a compound. So it's called a molecular compound because it's made of lots of molecules. There's also large extended structures, and this is a small piece of a sodium chloride, a salt crystal, which actually this would keep extending in all directions for millions and millions, and actually billions and billions of atoms long and wide and high. So that's another kind of compound that's an extended structure. So remember, pure substances. Oh, now we're going to talk about pure substance versus mixtures. A pure substance contains only one type of element or compound. That should say or compound. So if you have a whole lot of water molecules in a glass of water, but there's only water molecules there, even though there are two elements, every chunk of that water is made up of the same kind of molecules, so that would actually be a pure substance because it's made up of only one compound. Mixtures have multiple types of elements that are not in a compound form, or they're made of multiple compounds. So let's look at some examples here. One of the ways you talk about whether something is pure or not, or what kind of change it's undergoing, is whether or not something is undergoing a chemical change or a physical change. A physical change represents a change in state, but not composition. So if you have water and you heat it up, if you have ice, and you heat it up, it turns into water. So here you have water molecules, and they're all arranged very firmly. They don't move with respect to each other. When you heat it up, all of a sudden you have liquid water, and all these molecules are moving all over the place. They're jumping all around. Even though they're jumping all around, it's still water molecules, so it hasn't changed what it is chemically. If you heat it up even more, it becomes a gas. The water molecules are still they're still water molecules, but they're all moving around more separately. So this is called a physical change because it's changed its physical state, but it has not changed its chemical composition. If you do something like burn something, this is a picture of burning methanol. If you burn methanol, what happens is the methanol changes into carbon dioxide and water. The methanol and oxygen react to form carbon dioxide and water. So you've taken some chemical entities and you've made new chemical entities. Because the chemical entities have changed, you don't have the same stuff, you now have done a chemical change. So physical change is the same stuff in a different state. Chemical change is different stuff. The final classification we're going to look at are two types of mixtures, heterogeneous versus homogeneous. Remember, mixtures contain more than one kind of chemical entity mixed together. A homogeneous mixture has constant composition throughout. So here's some vinegar. Vinegar is made of water with acetic acid dissolved in it. And so if you take any sample of this water, of this vinegar, which contains acetic acid, it contains water and acetic acid, and it's the same composition everywhere in the bottle. It's not any different any one place than another place. So it's uniform, and so therefore that's a homogeneous mixture. A heterogeneous mixture has different things in different places. So here we have some spaghetti or something like that in a broth. And so if you look right there, you got spaghetti. If you look right there, you got broth. Different things in different places, heterogeneous mixture. Finally, you can look at what kinds of classification of matter you have by using a flowchart like this, where what you can say is if you have matter, what it can do is it can go to make substances or mixtures. Or it can make, this is pure substances. Pure substances are mixtures, so you can look at those first. If you have pure substances, they can either be elements or compounds. If you have mixtures, they can be homogeneous or heterogeneous. So if you have filtered air, air is really a mixture of oxygen, nitrogen, and argon. Those are the three main gases. If you have filtered air, it means it's only everything's in the gas phase, and then it'll be well mixed, so filtered air would be a homogeneous mixture. Filtered water, filtered means nothing floating around in the water, nothing dissolved in it. That would be a pure compound, because it's all just water. A gold bar is an element, because it's all made of the same single element, gold. And salt water has salt dissolved in water, and pretty much everything where you have something dissolved in something else is a homogeneous mixture. And that, I believe, is it. That is not it. I lied. So the final thing is that pure substances and mixtures can be separated from each other without changing the chemical composition, so you can just use a physical process. So for example, you could take salt water and you could just heat it up, and the salt would stay in the beaker and the water would leave. So now you would have water separated from the salt, but you haven't changed what they are. So you've taken a mixture and you've separated it by a physical process which hasn't changed the chemical composition. Chemical reactions are used to change compounds and elements. So you can take something like, for example, mercury oxide. If you heat that up, you can make mercury and oxygen gas. So you can do a chemical change to take a compound and essentially decompose it into its elements. And that is it.